Okay. Good morning. I hope you had a great weekend. So let us continue on our voyage through classical mechanics. And to begin with, we had some unfinished business associated with these non-inertial frames. So we reminded ourselves, because I think you had some idea, so a non-inertial frame, it's an accelerating frame, and one of the characteristics of such a frame is that to an observer in that frame, Newton's law, in particular Newton's first law, does not seem to be satisfied because there is seems to be an acceleration without a force, and therefore the observer in the frame has to invent a force, a fictitious or an inertial force, to try and explain what he or she sees. One famous example, of course, being centrifugal force, which you need to explain the tension in the string if you're an ant sitting on this bob as it is revolving. Now, we left on Friday this poor character here, the stick man with the very round head, in the free-falling lift. Okay, so that's an unpleasant situation to be in. But let's just have some comment on that. So, as I'm sure you sort of know, that from the point of view of this round-headed gentleman, he himself, and also a ball, if he lets go of it, everything appears to be weightless. Okay. So the lift has now become a purely inertial frame in all directions. But this is deeply troubling to this person because he knows about gravity, and so he has to invent some force, which is a fictitious force, which is that associated with the downwards acceleration, which is somehow cancelling out gravity. And very interestingly, the cancellation is perfect, and this is actually the equivalence principle which leads on to general relativity. But this is not in our prelim syllabus, but we can continue to consider the gentleman in the frame in the lift. And now consider the case where, luckily, he is not falling, but the lift is being accelerated upwards by some external force. Okay, so there's presumably some cable not drawn here on top of the lift, which is pulling the lift upwards. And in general it will be accelerating. And now let's try and examine how things appear both from the inertial frame and also within the lift itself. Okay, so there is a total force on the lift. This we can agree on. This is as evaluated from our inertial frame outside. Let's call this F total. And that is going to be this external force upwards minus mg, big mg, which is the mass of the lift, which is clearly downwards. That's gravity. So the acceleration of lift in the external inertial frame is just going to be nothing more than this force divided by the mass of the lift itself. Okay, so it's just A equals F over big M minus G. Okay, so now let's now switch to the lift frame. And consider the if the ball was dropped, what would the acceleration be on the ball? Acceleration of ball. Okay. So the key thing is that the floor of this lift is accelerating upwards with respect to the ball. And in addition, there is the acceleration downwards from good old gravity. So there's two components. And because the floor is coming upwards and the ball is being accelerated downwards by gravity, these will add, okay? So this is going to be, so we have F over big M minus G plus G. So this is the acceleration upwards of the floor. I mean, this is how we understand things to be as the external observer, because we know what's going on. But the guy in the lift is going to measure this acceleration, and the result he's going to get will be this summed with G, which quite obviously is gravity. Okay. And so this is F over M, okay. And this is, from the view of the person inside the lift, this is going to be downwards, right, towards the floor. Okay. So that's the acceleration of the ball. Now let's sort of turn it around and say, well, what about the weight of the ball? If he were to measure the weight, like if he weren't actually to drop it, but just to measure the weight with a spring balance, what would he find the weight to be? So the apparent weight of ball is just going to be this downwards acceleration times the mass of the ball. Okay. Which we call little m prime. So this, does this result seem to make sense? Let's check it in limits. So in the case where F equals 0, that means that there is no force pulling upwards. It's as if the cable has been cut. This is free fall. And then weight is equal to 0. Okay, so it's weightless. Okay, this seems to make sense because this corresponds to the discussion we were having on the previous slide about what happens if he's in free fall. What about in the case that the force upwards from the cable is just equal to mg? So that's the case where the cable is just stopping the lift from falling. So F equals big mg. Then the weight is then going to be given by big mg over m times m prime, which is m prime g, which is the weight it would have in the inertial frame, and it is in the inertial frame. So this is, again, makes sense. Okay, so this result seems to be a sensible one. But again, let's be clear. So the actual acceleration the observer sees for the mass, and therefore the weight he measures for the mass, is different from that in an inertial frame. It's different from that from gravity alone. There seems to be some inertial force or fictitious force which is causing it to be changed. Okay, so if it is dropping, how long will it take to hit the floor? So in lift frame, how long to hit floor? Well, we have the acceleration. The acceleration is constant. You can just dial up one of your simple school level equations of constant acceleration that distance equals the half AT squared So if it's dropped from a height h, height from which it's dropped, height above floor, then we get the result that T is equal to square root of 2h big M over big F. Okay, so this, again, to be clear, this is a different result in general from that if you just had gravity working. Let's now go back to the inertial frame. So we can view this as a frame external to the lift, but let's say the lift has transparent sides, so the observer is looking into the lift. How long would it take the ball to hit the floor according to the external observer? Well, in this frame, everything is working according to Newton's laws, and the situation which the observer sees is slightly different. He sees that the ball is released, and what is the acceleration of the ball downwards? Well, in the inertial frame, it is just given by gravity, g. But at the same time, this observer notes that the lift is accelerating upwards due to this external force and the difference between that and gravity. So the inertial observer sees the floor accelerating upwards, but at the same time the mass dropping in a completely normal manner. Okay, so can we just work out what the time at which it strikes the floor? Okay, so let's say that the symbols are defined here. So again, it starts at h above the floor, but by the time, but the ball does not have to fall that distance h because it's accelerating upwards. It only has to fall a distance h prime. Okay. So ball only falls h prime, and so the time it takes to hit the ground is given by just 2h prime over g. Okay, this is just a ball falling. But h prime is something we've introduced. Can we get some measure of what h prime is? Well, we know, I mean, h prime is there's a difference between h, which we know, and this h prime, and that is this distance here, and that's the distance which is covered by the lift accelerating upwards. Okay, so that must be given by, so again we can write a time expression, but the distance now, this is for the lift accelerating upwards, the distance is h minus h prime, and the acceleration is the acceleration of the lift. Okay, so that's just F over m minus g. So this is the lift rising term. Okay, is that clear? So we can solve this for h prime. So let me just tell you what the answer is. That h prime is just equal to big M g h over f. And then if we sub back in, we can find out what t is. And it's given by putting h prime into there, the square root of 2 big M h over big F, which, yes, that's just what we had before. So that's as before. So what is reassuring, because I mean, non-inertial frames are pretty weird, but they're not that weird, at least in classical theory, that the actual the causality of the events and the things happen at the same time, at least. Okay, so it takes the same time to hit the floor, whichever frame we observe it in, but through a slightly different interpretation of what's going on. Okay, we're going to come back to non-inertial frames later in the course, But today we now have to take a swerve into something which maybe should be covered by your previous lecturer, but I've drawn the short straw, which is the motion of charges in E and B fields. Okay. So this is going to be partly revision, but let's begin. So what is so our master? So as you know, the force of a charge in a B field, you should know, is given by Q, the charge, times V cross B. Okay. Yeah, incidentally, now we start to write cross products and things. I just have a tendency ingrained in me to write my cross product sign like this, but the more usual cross you'll see on the slides at least, so I hope that won't confuse you. So this you know, this is F is the magnetic force, Q is the charge, V is the velocity of the moving charge, and B is the magnetic field. And the key thing is that the force exerted on the moving charge is perpendicular to the B field and to its direction of motion. This gives rise to your left-hand Fleming rule and all such fun and games like this. One interesting consequence of this is that because the force is perpendicular to the displacement, the force actually does no work on the particle. Let's just be clear. The work done in general is given by F dot dx. Okay, this you remember from last term. So for a small path of dx in length under a force F, dw, the work done, is just given by that. Usually you've had this in a one-dimensional case, so you don't worry about the dot product. The dot product is to allow for the case where the force and the path are not parallel to each other. And this is the case here, because now if we substitute in what force is, we can write that as QV. And what is V? V is no more than dx dt. This is cross B, and this is dot dx. Okay. And so this vector, this is the velocity, that has to be in the direction of x, but you have a cross product between that and b, which must give you a vector which is perpendicular to both of those. And hence, if you dot product that result with dx itself, because this is orthogonal to this, you must end up with 0. Okay. So, so no work done, and the kinetic energy does not change. Okay, so the magnetic field, it just has the consequence of changing the direction of the particle, but not actually changing the magnitude of its velocity, not changing its kinetic energy. And if the initial value of V is perpendicular to B, then the particle will move in a circle. I mean, this you know already, but this is something which we'll now explore. So just, so in the case, let's go over here. So if V perpendicular to B, then firstly, so this is the firstly the simple treatment, and then we'll come back and do it with more rigor immediately afterwards. This is good to get a good sense of what's going on. Then the magnetic force is equal to the centripetal force. And so the magnetic force, so that's Q times V cross B, but V is perpendicular to B, the vector. So if it's perpendicular, then we can just multiply them together. And now we're going to be, because it's a simple treatment, it's a sloppy treatment, I'm going to be dropping all the vector signs. We just understood that the forces are at least in the right direction. So the force is just Q times V times B, and that's equal to mv squared over big R. Okay, so this is a centripetal force. So these are magnitudes. Okay, let's never forget that these things are vectors, but in this very trivial treatment, we will just be focusing on the magnitudes. So here, R is the radius of curvature. Okay, and so we can actually rearrange that and say R is equal to mv over qb, which is equal to the momentum over qb, where p is the momentum. Okay. So this is actually a very useful formula to have in your head, or something you can derive very, very easily. Interestingly, this expression is always true, even in special relativity. You know, in special relativity, that momentum is defined in a slightly different way, but once you've done that, that expression remains valid. So that expression is good enough to calculate the bending of the ultra-relativistic protons in the Large Hadron Collider, in the magnets of the Large Hadron Collider. So even though you're in a very relativistic regime, that formula holds. Okay, so those of you who are more rigorous, let's try and look at this in a slightly more thorough manner. And this will involve setting up and solving simple differential equations. Okay? So we have from Newton's second law that mr double dot is equal to whatever the external force is. So that's a vector equation. So this gives three equations. So this, and these are obviously that mx double dot is equal to f subscript x, my double dot is equal to f subscript y, mz double dot is equal to f subscript z. So I'm using this double dot notation for the second derivative to tell me what acceleration is. So what are the forces? So let's say we have, well, we know, here we have only a B field. Have B field only. And also, you're actually told, I did not yet stress this, well, it was clear on the previous slide, but it's pointing perpendicular to that plane. So this is the xy plane. So the B is pointing in the z direction, okay? So also B is equal to B subscript z k, okay? So it's only pointing in the z direction. Right, so we need to, this is the force which the particle will actually experience. So F is given by Q V cross B, which is going to be given by Q times Now we need to evaluate what V cross B is, so let me write down this determinant I, J, K, the start at the top. V, so that's, in my notation, that's X dot, Y dot, Z dot, and B, as we've learnt, only has a component in the Z direction. So if we expand this cross product, it's a simple one. So it's Q times Y dot BZ I minus X dot BZJ. So these are giving, my Newton's second law, I need to know what MR double dot is, and this is giving me the information. But first thing we note is that there's an I component and a J component. Well, let's just write this out explicitly. So MX double dot is equal to, therefore, QY dot BZ. My double dot is equal to minus QB, or minus QX dot BZ, and then MZ double dot is 0 because there seems to be no force in the Z direction. So these are our equations of motion, and then we will solve them. Okay. So let's first dispense with the most trivial of these. So that's the bottom one. MZ double dot equals 0. So you can integrate this, and so that means that Z dot is equal to a constant. But the constant is 0 because it starts at rest. You see, here are the boundary conditions, the initial conditions. The velocity is there. There's no velocity in the Z direction. So that's equals 0. Because that's the case at t equals 0. And you can integrate it again, and Z equals a constant. But it starts again at Z equals 0, so that is equal to 0. Okay, so Z equals 0, trivial. Right, the more interesting ones. We have MX double dot and MY double dot. So I can write, let me rewrite these as X double dot equals omega Y dot, and Y double dot equals minus omega X dot. What is this mysterious omega? Well, it's something I'm introducing with a nod to where we're going, where omega is just equal to QBZ divided by M. Okay. And I think you know where this is going, but this actually, if you look at this, this has dimensions of 1 over time, and this is actually called the cyclotron frequency. You'll see that cropping up. Okay. So we can we can start with either of these. Let's start with the bottom one. So if we integrate the Y double dot equation, we get that Y dot equals minus omega X plus C. C is a constant. Y dot is a velocity, but again at t equals 0, we know that the velocity in the y direction is 0. And this is 0 because y dot at t equals 0 is equal to 0. Okay. So we just have y dot equals minus omega x. Okay, so now let's put that back into the x double dot equation. So sub into x double dot equation, and we end up with x double dot plus equals minus omega x. This should be omega squared. Yes, that was quick work. Didn't give me a chance. It's just this point here, right? Yeah, thank you. That's a genuine. I can respect that. but I've only brought one of these Mars bars to the game, so I better not make any other mistakes. And can I find this guy? Yes. So who's that? Oh, it wasn't you again. All right, thank you. Right, okay, you're like the voice of doom sitting on my left-hand shoulder. Okay. Right, anyway, that's an important point. So, yeah, this is clearly simple harmonic motion. So this is SHM. And you know what the solutions to this are. I mean, you will have explored this to death in your maths course, and you knew before then. So it's given by a superposition of a cosine and a sine-like solution. So A1 cosine omega t plus A2 sine omega t, where these are constants set by initial conditions. Right, and what are the initial conditions at t equals 0, x equals 0? So this tells me that A1 is equal to 0. So we have that x equals A2 sine omega t. We need some way of fixing what this A2 is. Well, we know about the velocity at t equals 0. So let's differentiate this. We get x dot equals omega A2 cosine omega t, which equals omega A2 at t equals 0. Okay, so t equals 0, the cosine goes to 0, which is equal to u0, because we're told that. So this tells us that A2 is given by u0 over omega, and hence we are almost there, that we have now that x is equal to u0 over omega sine omega t. Right? Yes. Now we want to find out what y is, so we now we have before we had y dot is equal to minus omega x, so that's given minus u0 sine omega t. So we can integrate, so y is going to be given by u0 over omega cosine omega t plus some constant, and because y equals 0 at t equals 0, this constant you will see is given by minus u0 over omega. Hence y is equal to u0 over omega cosine omega t minus 1. Okay, so we've got x and y. So we had z already. Z was trivial. let's just make the further small step to actually understand what this means. Let's rewrite, yet again, rewrite this as x equals r sine omega t, where r must be u naught over omega, and y is equal to r cosine omega t minus 1. And this last equation, I can just take this minus 1 to the left-hand side, so I have y plus r equals r cosine omega 2 omega t. So this equation for x and this new equation for y, let me square and add them. So that gives me x squared plus y plus r all squared, and that's going to give me r squared cosine squared omega t plus sine squared omega t, and this is by trigonometrical identity, this is equal to 1, so you just have r squared on the right hand side. Okay, so this is, we have x squared plus y plus r all squared equals r squared, so the motion is that of circle. Centered on x equals 0, but y equals minus r z, with radius r. Okay, so this we've now shown in a slightly more thorough way with that which we initially here just waved our hands around and said it must be so, and it must be so, but it's nice to see that the equations tell us that. What about if everything was the same, so the B field's still only in the z direction, but the only thing that you were to change was that as well as having a slight motion in the x direction, you started with some velocity also in the z direction. What would happen? Well, in that case, nothing would change in the sense that there's no force acting on the z direction. This is still not the case, right? So there's still no force in the z direction. So in the z direction, the particle would just obey Newton's first law and just continue with constant velocity. So it would tread out a distance of w0 times t, whereas what you have in the x and y plane would remain the same. So it's just it would just be an identical result, but moving upwards. So what that is a spiral or a helix. Okay. So the result is obvious and just a small generalization of what we had already. All right, so we can do that. Let's now consider the case where we add something else into the game, which is an electric field. Okay. So with an electric field, we have mr double dot is equal to qv cross b. And then what force does an electric field exert on a particle? It's just Q times E. You know that. So we just have the superposition of this and what we've been discussing from the B field. But putting all of that together, that has a name, and that is sometimes called the Lorentz force. The combination of both effects. Okay, so let's analyze the situation. So the situation is as before. So the situation is as before, So the B field is still in the Z direction, but we've got the E field, and this is coming in the X direction, as you see from the diagram. And the only other thing I draw your attention to is that we start completely at rest. Okay, so that is new. In the previous case, it started with a velocity in the X direction. I mean, if we had analysed the previous situation when it was starting at rest, it would have been a very boring problem because nothing would have happened, because the B field needs the particle to be moving to actually exert a force. But here with the E field in the game, these will work together for something interesting to occur. Right, so let's analyse this. So we want to write down the equations of motion. So what are the forces? So the contribution to the force from B is just as before, right? Because nothing's changed here, in that we have the you have the Q V cross B equals Q Y dot B Z I minus X dot B Z J. So that's just a straight copy of the previous board. But if we now, again, let's just get rid of the, let's forget about at the start the Z component. Again, we'll find that Fz equals 0, so Z equals 0. So we don't need to worry anymore about the actual Z equation of motion. That's too trivial. But what do we have for X and Y? So we have so for the equations of motion, we have that mx double dot equals qbz y dot. This is just as before, but we now have the E field in the game, and that is operating in the X direction. So plus q EX, right? And then the my double dot is minus Q BZ X dot. Okay, so let's see if we can keep our head and solve these. So we have, I start with manipulating, let's rewrite these again, making use of my omega, the cyclotron frequency. So I have X double dot equals omega Y dot plus QEX over M, where omega equals QBZ over M as before. And the Y equation of motion is just Y double dot equals minus omega X dot. Okay, is that right? Yeah. So let's focus first on the bottom one. So it's the same sort of approach as before. I'm going to integrate. I get Y dot equals minus omega X plus constant, and that is equal to 0 since Y dot at t equals 0 is equal to 0. Okay? So Y dot is equal to minus omega X. Okay, now I can put this back into the X double dot equation, and we get X double dot plus omega squared x, I remember it this time. I'm putting this on the left-hand side. But we have this initial term, this second term, which we did not have before, which I'll leave on the right-hand side, as QEX over M. So this is a slightly more tricky differential equation before, because this is a non-homogeneous differential equation. But you know how to solve these. You've been practicing these for a long time, I have no doubt. So, so firstly, we have the solution is x equals x1, where x1 is the solution of the complementary function. I'm not out of sync with your maths, am I? You've done complementary functions and stuff. Good. There's a gentleman in the front row who's nodding at me. Plus x2, which is the particular integral. Sorry, I'm dying here with coronavirus, but I think I can get through to the end of that's a joke, but I do have colleagues in Wuhan, so I feel sorry for them. Well, at least I hope it's a joke. Okay, so this is so x1, as usual, is before it's just a superposition of a cosine and a sine term, whereas x2 we just need to look at that and try and think of some trivial solution for x which does the job, and something which does the job is clearly just the constant x equals QEX over m omega squared. Okay, so that's a constant solution for x, which if you put it in this equation will work. Okay, so so we have, therefore, that x equals a1 cosine omega t plus a2 sine omega t plus QEX over m omega squared. Let's call this. So we keep on defining more and more new parameters, but let's define this as A, okay? So I have x equals a1 cosine omega t plus a2 sine omega t plus a. So all we now have to do is to put in the initial conditions to find a1 and a2. So at t equals 0, x equals 0, this tells us that 0 equals a 1 plus a, and at t equals 0, what else do we know? That x dot equals 0, and this, if you work this through, that will tell you that a2 equals 0. So without labouring on these last points, I find that x is equal to a1 minus cosine omega t. Okay, I want to at least get to the bottom of this slide before we finish. Now we need to, we had from before, we had that y dot is equal to minus omega x. So we put this in minus a omega 1 minus cosine omega t. So we integrate y is equal to a sine omega t minus omega t plus some constant, and I hope you can follow where we're going. I'm going to make use of this piece of board we have here. What is this constant at t equals 0, y equals 0? This means that the constant is equal to 0, and therefore we have y equals a sine omega t minus omega t. Okay, so we have solved the problem, but let's just try and put some interpretation into it. So again, we can rearrange such that we have let's arrange so we just have the cosine omega t on the left-hand side. So we have that a cosine omega t is equal to a minus x. We call that equation 3. And here we have a sine omega t equals y plus a omega t. That's equation 4. If I square 3 and 4 and add them, again we benefit from the usual trigonometrical identity, and we get that a squared equals x minus a squared plus y plus a omega t squared. Okay. So what does that mean? Well, you can squint at this for a while, but you see, again, it's a circular motion, but it's a circular motion with a cute twist in that, okay, so the radius of the circle is a, which we defined here. In the x direction, the centre of the circle is x equals a, but in the y direction, the centre of the circle is not constant, it's evolving with time. It's evolving steadily in time. So it's at y equals minus a omega t. So it's like a circle which is rolling down the x-axis. So the particle itself, if you try and map out what the particle does, it starts here, it will roll out to there, accelerating, and then it will roll back inwards to here, stop, come out again, back again, etc., etc. So this is a very non-trivial behaviour which comes from the superposition of both the E and the B field. High time to finish. So assuming I'm still alive tomorrow morning, I've not been taken into quarantine, we will just finish by considering the kinetic energy of these, this case and the case before moving on to torques and angular motion. Thank you.